We often take everyday living for granted, being healthy, active, and having the opportunity to participate in the things you enjoy. It's something most of us don't even think twice about. However, for someone with a neurological condition, this can be very difficult. Imagine waking up one day and suddenly, your vision is gone completely blank. This was the experience of a friend who was later diagnosed with multiple sclerosis and is likely a representation of many others. It shows how quickly conditions such as multiple sclerosis, MS, and amyotrophic lateral sclerosis, ALS, can affect your life. ALS and MS benefit greatly from early diagnosis, but due to the nature of disease, they undergo a plethora of testing before diagnosis that can sometimes last from months to years before there are answers. This also costs a lot, as they need to go to many different specialists, undergo different procedures, and can cost up to tens of thousands of dollars for people living where health insurance is not insured. Furthermore, 80% of patients who are diagnosed with ALS die within 2 to 5 years of diagnosis. Around 90% of ALS cases have no known family or genetic cause. Our solution is to create a nanoscale biosensor that can detect biomarkers of these diseases. These biomarkers include TDP43, which is indicative of ALS, and CHI3L1, which is a protein similar to TDP43 but for multiple sclerosis. We will also observe the presence of neurofilament light chain, which is indicative of neurological disease. Together, these biomarkers will hopefully give us a better diagnostic reading with only a spinal tap, meaning that these patients only have to go see their family doctor or general practitioner to get a referral, and this can be done in any clinic, outpatient, hospital, or even in the doctor's office. The goal of this is not only to reduce costs, but also to reduce time and increase accessibility. Looking at our UN sustainable goals, something that we want to focus here is number 10, reduced inequalities. By making an affordable solution and accessible healthcare, we can get more people proper diagnosis earlier and therefore better treatment and quality of life. Our project really focuses on the UN sustainability goal number 3, good health and well-being. This is done by streamlining the diagnostic process and proactive healthcare so that patients can get the best quality of life and the best treatment options possible. The project aims to help get people the diagnosis when they first start exhibiting symptoms. For ALS, it is a progressive disease, so our product could be implemented at the first sign of symptoms, such as muscle weakness or numbness. This project aims to help people get the diagnosis they need quicker and cheaper, making it more accessible to those that may have barriers. Our design was based off of our project from last year, where we aimed to create a nanoscale biosensor able to target Alzheimer's disease. We were successful in creating a base for our sensor, such as the vesicle and the nanopore that will hold our detectable signal, but we struggled in aspects of stability and modularity. This year, we'd like to grow from what we did last year and work on fixing that so this can become a real-world application. Something that we'll be changing is going from an RNA-zyme to a DNA-zyme. These are synthetic catalytic components of DNA or RNA that can self-cleave. Since RNA is inherently more unstable and it self-cleaves, creating false positives more often, our change to a DNA-zyme is hoped to create a higher level of stability in biological solutions. This can also be further achieved by using non-natural functional groups and adding those on for further stability. We'll also be changing our detection method. Moving from a fluorescence-based detection, we will be using an ion-based detection, which offers a cost-effective, real-time, and label-free approach to measuring the biomarkers by measuring a change in signal. This, unlike fluorescent-based methods, does not require expensive antibodies or dyes, and it reduces the reagent costs. Our final change to our previous design will be the implementation of allosteric toehold-mediated strand displacement. This will allow for our biosensor to target different biomarkers without creating a brand new biosensor. This is done through a very controlled process of introducing new DNA strands to our DNA-zyme and exchanging something called a toehold, which is a free single-stranded piece of DNA that actually binds with the biomarker and signals the presence. This opens up the possibilities of not just targeting the biomarkers that we're looking for, but having future applications in multiple neurodegenerative diseases once we find biomarkers for them. This works into UN Sustainability Goal number 12, responsible consumption and production. By minimizing our medical waste and having efficient resource utilization, this will create a much more modular design.